Okay, what we're going to look at in this video is AP Practice Problem H. It's another table question. We'll look at how to get the answers and the point totals for doing so. Like I said, it starts off with a table. It gives you X values at selected values within the interval from 0 to 6, and it gives you the derivative f prime of x. So these are basically whatever f is, these are some slope values at given spots. So starting off, they do tell us something about f, besides telling us about some points on its derivative, tells us that f of 0 is 20. So we know f prime of 0 is 4, but this is the actual y value for the original function. So f of 0 is 20, and the first derivative satisfies this inequality, meaning that the first derivative is never greater than 7. It's either 7 or it's never lower than 0. So it's pinned between 0 and 7 included. All right, so that's going to come into play in one of the questions. So they're telling us that, and you can see in the table, it never does leave that range, but they're guaranteeing us that that's the case because we don't know what's happening in between these. So even though we don't know what's happening in between these, we know they're between 0 and 7. So it says that's true for all x in the closed interval from 0 to 6, which is what we're talking about in this table. And once again, they tell us selected values of f prime are shown, and that f is has a continuous second derivative for all real numbers. That's just to guarantee us that the second derivative is at least good to work with from a continuity perspective. All right, so with all that in mind, let's take a look at problem A. Problem A says to use a midpoint Riemann sum with 3 subintervals of equal length indicated by the data in the table to approximate the value of f of 6. So there's some layers to this. The first is doing the midpoint area. Normally with these table problems, they normally can't ask the midpoint area because, what's the midpoint of 0 and 1? Well, it's 0.5. And you don't know the value of 0.5. But they were clever here because they said 3 subintervals. So if you go 3 intervals that are equal, you can go from 0 to 2, 2 to 4, and 4 to 6, and then your midpoints are 1, 3, and 5. So you can know the values of the midpoints if you make it 3 intervals. They want us to do all this to get f of 6. So it's very important to use this formula that says, well, if you want a function value, the problem is we don't know what f of 6 is. Well, we do know what f of 0 is. And this formula comes up a lot. It's derived from the fundamental theorem of calculus that if you want f of some value, you can use a different value so long as you add from the value you have to the value you want the integral of its derivative. So this formula says I can find f of 6. I'm going to take f of 0 and integrate from 0 to 6 of f prime of x. Now, it does say to approximate because I can't find this exactly because I don't know the formula for the derivative. However, it says approximate this area using the 3 subintervals of equal length and the midpoint approximation with those rectangles. So this thing is going to get approximated. I did it over here to draw a little picture of it. Here are my 3 intervals, 0 to 2, 2 to 4, 4 to 6. The midpoints of those intervals are conveniently 1, 3, and 5. So if I'm going to make midpoint rectangles, I want them the width of the interval, so they're all width 2. And I want them the height of the midpoint. So the height of the midpoint is given, because this is the derivative. I said I want to integrate the derivative. So the derivative at 1 is 3.5, the derivative at 3 is 0.8, and derivative 5 is 5.8. Now I can use those as heights and draw on the 3 rectangles. So what is the approximation for this area as best as I can get it? It's these 3 rectangles added together. So show the base times the height. So there it is, base times height 1, base times height 2, and base times height 3. Remember, all the bases are the same. The heights are just based on those midpoints. So this thing gives me an approximation of this. This is exact. So I did put that all of this is approximately, as best as we can tell, it's these 2 pieces. And this piece is 20. This piece comes out as 20.2. Add them together with 40.2. So what is f of 6? Our best guess for what the function value is at 6 is 40.2. All right, so that answers part A, and you can see the point values here. There's a point for using the fundamental theorem of calculus. There's a point for basically doing that midpoint rectangle setup, and then there's a point for the final answer. Technically, due to the AP simplification rules, if you left it this way, you should get both points because not only did you show the work for the rectangles, but since you didn't have to simplify, you don't actually have to turn it into this. So that line should get you 2 points. All right, so part B says, determine whether the actual value of f of 6 could be 70, and to explain your reasoning. Answer's no, but the important part's why, because you could just guess yes or no, 50-50 shot. Why can't it be? Well, it comes back to this formula. Basically, what can I know about f of 6? I know it's f of 0 plus this integral. Now, remember, I didn't know what this integral was exactly. I approximated it. But the question then becomes, since this is locked at 20, what does this integral become? Could this integral be 50 or larger? The approximation says it's only this, but once it gets approximation, it's probably wrong. Is the true value able to get us over 70? So I'm saying no, that's not the case, and here's why. It comes back to this fact they gave us. It's important that you read this because then you know that the derivative can't exceed 7. What that does for me is I'm going to talk about that integral. So what's true about this integral from 0 to 6 of f prime of x? What's the biggest it could possibly be? Well, here's a little picture of it. I drew, here's f prime of x, some weird sketch of it. It's probably not maxed out, but what would it look like if it were as big as possible? Well, the derivative, the tallest this derivative could be is 7 essentially everywhere. Now, we know it's not actually 7 everywhere, but it could just instantaneously kind of very quickly drop to these spots. It could be 7 through most of this interval, just dip down on occasion. But let's assume it doesn't even do that. Let's assume it is 7 all the way across, which it's not even that. But if it were 7 all the way across, well, remember the integral gives area. So if we look at the interval from 0 to 6, and this function height is 7, what could the area of this be? Well, the biggest area you could possibly have is this thing up at 7 and this thing being 6 wide. So I should say this way, up at 7 and 6 wide. The biggest it could be is a rectangle that's 7 times 6 or 42 square units. The integral is probably not that big, but that's the largest it could possibly be. You're stuck at 42 square units in here. So now I can combine that information with this to basically say, well, if this thing can only get up to 42 and this thing's 20, well, the biggest this can come out is 20 plus 42, which is 62. So now to read what I said, I go, no, since the greatest f prime of x can be is 7, the greatest, the integral from 0 to 6 of f prime of x can be is 6 times 7, or 42. So hopefully you see where that logic's coming from. Basically, the biggest area is that rectangle it could form. Now I go and say, well, since f of 6 is f of 0 plus that integral, the greatest f of 6 can be is that 20 plus that maximum area 42, which is 62. So if the maximum can be 62, it's less than 70, and f of 6 then can't become large enough to get to 70. All right? So kind of an interesting problem. It's a little difficult to sort of break it down, but once you do, once you kind of realize this thing's happening, what is the maximum area, you realize the maximum area can't bring you where you need to go. So the points for this are something about the boundedness and the reasoning. So the boundedness is, what is it bounded by? It's can only get up to 20 plus 42. So basically reasoning this 42 or together the 62 gets you something, and then the reasoning from there gets you that second point. All right, so there's part B. Part C should be an easy question if someone really understands the fundamental theorem of calculus. How do you evaluate an integral? Well, you take its antiderivative and plug in. So how do you evaluate the integral from 2 to 4 of f double prime of x dx? Well, you need f double prime's antiderivative. F double prime's antiderivative is f prime. So I'm evaluating its antiderivative from 2 to 4. So that means I have to plug 4 into the antiderivative, or 4 into this f prime of x, and 2 into this f prime of x. This is literally the fundamental theorem of calculus. They just threw a second derivative in here to make your antiderivative the first derivative. Now that you know that this thing's equivalent to f prime of 4 minus f prime of 2, well, you need those values, and that's what the table comes in really handy for, because it gives you basically what are the f prime values that you need to know. You can look up 2 and 4 right out of the table. I plugged them in, 1.7 minus 2, which gives me negative 0.3. So the points are allotted to the fundamental theorem of calculus, realizing the antiderivative, and then to the value itself. And once again, do the simplification stuff. Once you get numbers, you could leave it. So technically the answer could just be left this way. Last problem is a limit. Typically limits, if it's an easy limit, you just plug in and get the value. But AP's never going to just make it that easy, right? They got to put some twist on it. So what they're going to do is they're going to give you a limit, and it's going to come out indeterminate. So we have to verify that, though, before we go on to find the answer. So what is the limit as we approach 0 of this mess? Well, have the x go to 0, basically plug in 0, see what happens. Well, if we plug in 0, we get f of 0, 20e to the 0, 0.5 times f of 0, and then that minus 10 stuck that way. So now that the 0 is all plugged in, e to the 0 is 1, so this is just going to stay minus 20. I'm going to need to know what f of 0 is for the other ones. Well, f of 0 was given to me in the problem. If you read carefully, you realize, oh, I know what f of 0 is. They told me it was 20. So I come back and go, well, I know f of 0 is 20, and here I know f of 0 is 20, and I basically get 20 minus 20 is 0, and this is half of 20, which is 10 minus 10, which is also 0. So the limit, when you plug in, this gives you an indeterminate form. It gives you 0 to 0. So the limit's not equal to this. This basically tells us we don't know what the value of the limit is because plugging in isn't working. So what do we do in this case? Well, the best tool for indeterminate form is L'Hopital's rule. So what you're going to do is look and go, well, I got 0 over 0, that's indeterminate. L'Hopital's rule says if it's indeterminate, I can just take this original limit, do the derivative of the top, and do the derivative of the bottom, and plug in again. And this thing's different from the original, but the limit as it approaches this will turn out the same. Basically, what was proven with this theorem was if you do that, if you have something indeterminate, when you take the derivative of the top and the derivative of the bottom and re-plug in, if you can get a value out of that, it has to be the same as the value of what this was. And don't mistake doing L'Hopital's rule for the quotient rule. We're not getting the derivative of this thing. L'Hopital's rule just says if you want the limit, it'll be the same if you do derivative of the top, derivative of the bottom. Because normally we can't just do derivative of top, derivative of the bottom. But in L'Hopital's rule, because we're doing a limit and not finding a derivative, it works out. So here's my L'Hopital's rule applied. Plug the 0 in. Well, now I got f prime. Well, let me explain where I got this thing. Derivative of the top. Well, derivative of this part's f prime of x. Derivative of this, well, the 20 comes along for the ride, and e to the x is its own derivative. Down here, this is just a number on the f of x, so we don't have to do the product rule. It just comes along for the ride. I get the 0.05. F's derivative is literally f prime of x, and then the minus 10 becomes 0. So now that I have the derivative of the top, derivative of the bottom, we'll throw the 0 in, f prime of 0, 20e to the 0, and then 0.5, f prime of 0 again. Well, now we need... well, this comes out as 1 times that minus 20, so that's fine. Now we need f prime of 0. Once again, we know that. F prime of 0 is sitting right up here. F prime of 0 is 4. So we come back and we plug those in. We go, well, we have enough information. We have the 4. This is half of 4, which is 2. And all told, it comes out as negative 8. Points on this. You have to get to using L'Hopital's rule to get a point out of this thing. Sometimes they'll give you a point for the indeterminate form and then for the usage. In this, it seems like they just looked at the limit and go, hey, if you know to use L'Hopital's rule and do it correctly, there's your point, and then generating your answer is your last point. Once again, due to simplification rules, once you plug into the function, if you get this numeric answer, you can just leave it. All right, but those are the answers, and those are the point values, and that's how the answers are obtained. Once again, it's a good mix of problems. It's got limits using L'Hopital's rule, some fundamental theorem of calculus. This one's a little strange, but it's a thinking question, I guess. If you can figure it out, good for you. And then this one, the mix of the, like I said, the clever way of incorporating midpoints, because normally with tables they can't do midpoints, but they found a way to get midpoint in here along with this very important integral function evaluation rule from the fundamental theorem of calculus. So a good array of stuff in here. All right, well, that ends this. Up next will be AP problem I.